Hello, everybody. What we're going to be doing in today's lecture is we're going to be looking at Taylor and Maclaurin polynomials. All right. What are we going to be doing specifically? Well, we're going to learn what a Taylor or Maclaurin polynomial is, first of all. All right. We'll look at some pictures, that kind of thing. After we do that, we're going to learn how to compute the Taylor or Maclaurin polynomial. Learn to compute Taylor and Maclaurin polynomials. All right. We are going to learn what a Taylor series is. We're going to learn the definition of Taylor and Maclaurin series. No, not Siri. Man. Learn the definition of Taylor and Maclaurin series. And that's about it. So a lot of what we're going to be doing in here is going to be relevant for the next, 2 lectures after this one. So it's really important that you get the basics here down pretty well. Okay, you definitely have homework on this that you need to work on. Okay, so let's get started. So here's the idea. In Math 4B, no, that's the one you're in now. In Math 4A, you learned the idea of a linearization of a function. So you learned about linear approximations of functions. All right. Now, what is a linear approximation? Well, like basically given in f of x and in a, so in a was where you were going to find the linearization about, you can find this thing, which I'm going to just write out here, L of x equals f of a plus f prime of a x minus a. And this L of x was called the linearization of f of x about x equals a. So let me write that. Which is the linearization, which means the best linear approximation of f of x. Actually, I'll put that there. So the best linear approximation of f of x centered at or about x equals a. Okay, and we're going to be doing a lot of calculations of this kind of thing later on. So I'm not going to calculate one right here, but I'm going to give you an example. So here's an example of one. So let's see, the linearization of, let's say, f of x equals sine x, a simple function, about x equals 0 is this one. L of x equals x. Okay, so not a very complicated linearization there, but that's what it is. Now, what does that mean? All right, so the idea here is this. If I go to Desmos here, we'll look at a graph. Is if I graph y equals sine x, function sine x, there's a sine function, right? Let's make that a little bigger. Okay, so there's a sine function. And of course, at 0, you're at 0, 0. So there's a dot right there. Label 0, 0. Now the linearization we just found out was just y equals x. Very simple linearization. There it is. Okay? But what you're supposed to notice about this, come on, let me change it. I just want to change it. Thank you. What you're supposed to know about this, or notice about this, is that the two curves are very close together here. All right, so if I, how would I do this? I don't know, I'm not smart. Copy, no, that won't work. Save, let's save it. Export image, download PNG. Download. Quit. If I go over to my notes now, let's put that here. We can do that, right? We are very smart. That's a calculator. Oh, you can't even see it. But I just tried to put a calculator there because I don't know what app is what. There we go. All right. More work than it should have been, but there you go. There's a graph of it. Okay, and the reason I wanted it here was I just wanted to make the point that the curve y equals x here and the curve y equals, come on, I'm trying to write here. Let me write. Y equals sine x, the red curve, are close together as long as you're close to this point 0, 0, right? Like in a little region around here, from here to here, the functions are very close together, right? Like the curves are almost overlapping in that little section. So in here, close to x equals 0, the curves are close together. All right? So we could say that y equals x is an approximation of y equals sine x. It's not good everywhere, but in the little section of the graph, they're very close together. Okay? And so y equals x is what we would call the best linear approximation of sine x for x values that are near x equals 0. Okay? And that's all something that, in theory, you already know about. Okay? You know about linearization already. So what we want to do is extend this idea to functions that are maybe not linear, right? Like here's a linearization, but what can we do? A second degree, third degree, fourth degree? Extend that to higher degree polynomials? And the answer is yes, we can. And that is what we're going to call Taylor polynomials. All right, so let's get started here. So let's see. Taylor polynomials. That's not quite right. Polynomials. All right, so the Taylor polynomial centered at or about they'll say about x equals a. All right, so the Taylor polynomial centered at x equals a of degree n, I'll say for f of x of degree n. We have to get all that in there. Degree n is computed, or is, this is the formula for it, this. So we're going to say, call it p subscript n. I think your book uses a lowercase p. A lot of other books use a uppercase. It doesn't matter though. So p in x. So you can see that you put the in there. That way, if you see p3, you know it's going to be degree 3, that kind of thing. So p in x is going to be given by this formula. So it actually starts out the same as the linearization. You go f of a plus f prime of a, parentheses, x minus a, then you go up to the next one, f double prime of a over 2 x minus a squared. And actually, I'm going to start putting in factorials here. 2 is 2 factorial. The next term is f triple prime of a over 3 factorial, then x minus a to the 3. And you just keep doing this. I ran out of room, but where you're going to stop is when you get to the nth derivative. So f in there is not an exponent, that's the nth derivative. Divide by n factorial, and then x minus a to the n. Okay, and that is the Taylor polynomial. All right. Now, what is it though? So what it is it's going to be the best polynomial approximation of your function of degree n that you can get around a certain point. So let's say that Pnx is the best degree n polynomial approximation of f of x for x values near x equals a. Now, it's important that we say that. It's only good for x values near x equals a, right? Like if we go back to Desmos real quick and you say, okay, well, if you're zoomed in, those curves are very close together. But if you zoom out, those curves are very far apart. Okay, so over here at x equals 8, you know, the functions are very far apart. But over here at x equals 0, the functions are, whoa, didn't know I could do that. Over here, the functions are very close together. So whether they're far apart or close together depends on how close you are to the point where you actually did this approximation. And so we did it at 0, or at least I did. I didn't tell you that, but we did it. All right, so let's go back to our notes here. So Pnx is the best n-degree polynomial approximation of f of x for x values that are near x equals a. Now, one thing you probably want to know is when we say best, what does that mean? Why is it the best? And so when we say best, that's trying to write with the highlighter again. Put like a little asterisk there. So Pnx is the best in the sense that it is the only n-degree polynomial for which the following is true. So the idea is this. So we've got two functions, right? You've got this Pn of x, and you've got the original function, the real function, f of x, right? And so what we're going to do is we're going to say that what the Pn does, that no other polynomial does, is that when you plug in a into the polynomial, that's the same as what you get if you plug a into f of x, right? That's what you see here. That's why the two are overlapping at 0, right? Because they match the function value right there. That's the wrong thing. So they match. Now the other thing that's true, I can just use this graph, it's closer, is that you'll notice that not only are the function values matched, we also matched the slopes, right? Like the slope of the green curve and the slope of the red curve are equal, but they're only equal right here at 0. But that's the next thing that happens, is that Pn prime of A, that's the slope, is actually equal to f prime A. All right? Now that's all that you have if you're looking at the linearization, but we're not looking at the linearization, right? We're looking at degree n. So what you get for going to higher and higher degrees is that every time the n goes up by 1, you can make another derivative equal to the derivative of the original function, right? So you can continue this pattern on, and Pn, the nth derivative evaluated at A, is going to be f with the nth derivative evaluated at A. Okay, and so this is the only polynomial that will make all of that happen. Okay, and so when we say best, that's why it's the best. We're trying to approximate the function f of x, and the way we do that is by making all of these derivatives equal to each other, and that's how we approximate the function. Okay, now you can actually do this kind of like, we have a formula for the linearization, and then we can say, well, what's the formula for the best quadratic approximation? What's the formula for the best cubic approximation? What's the formula for the best fourth degree approximation, etc. But I don't think we really gain very much by doing that, and it takes a long time to do. So I'm just telling you that this is how you do it. The reason that Pn is a good approximation of f is because all of these derivatives are equal to each other. That makes the graphs look alike. Okay? That's kind of the key here. That making this happen, this makes the graphs look alike. Okay? So that's the idea behind a Taylor polynomial. All right? Now, in order to do anything with this, we're actually going to have to do a bunch of calculations. So let's do that. So I am cutting this out. You can't see it, but I am. Duplicate, bring this down here. All right, so here's my formula for Pn. And what we're going to do now is we're going to try to use this to calculate a Taylor polynomial. A lot of your homework is just calculating Taylor polynomials. So this is what you need to be learning how to do. So let's try it. So example. We won't start too hard here. Example. We are going to compute P3 x centered at or about, I'll say about x equals I'm going to go pi. So compute P3 of x about x equals pi for f of x equals sine 2x. All right, is that everything we need? I think that's everything we need. All right, so you want to pay close attention to this example because I'm showing you what I think is an efficient way of computing this. Okay, so how would we do this? I'll put another line up there for balance. Okay, so how would you go about this? So the first thing you have to do is make sure you know what everything is called. So one thing is this. So when they say about x equals pi, what they're telling you is the a value, but they almost never call it a. So you have to know that when they're giving you that value, that's the a. Okay, so before we start, we know a few things. First of all, we know what degree polynomial it is. 3. Okay, and we know what the a is. A is pi, and of course we know what the function is. The function is sine 2x, right? So make sure you have all of that straight in your head so you're not confused about it later on. Okay, now let's look at the formula for the Taylor polynomial and think about what you actually have to plug in to make this work out. So what you're going to need to use this formula is a bunch of numbers. So like a is pi, right? So f of a, that's going to be a number. You're going to need to calculate that number. F prime of a, that's going to be a number. We're going to need to calculate that number. F double prime of a, that's a number. You're going to need to calculate that number. F triple prime of a, that's a number. You're going to need to calculate that number. And we'll actually stop there because we're only doing a third degree polynomial, so we can just pretend that the rest of that doesn't exist. So we're going to need numbers for all four of those things. The other thing you're going to need is, of course, you do have these a's here, here, and here, and there's no calculations there. You just put those in, all right? So those highlighted things are what we're going to need to put in as numbers, and then we'll have P3. All right, I'm going to write out P3 actually. So P3 is this. P3 is, in general, f of a, f prime of a, x minus a, f double prime of a, 2 factorial, x minus a squared, and then f triple prime of a, 3 factorial, x minus a, 3. Notice how the numbers always agree. Like there's a 3 factorial, third derivative, third power, 3, 3, 3, 2, 2, 2, 2, 2, 2, 2. All right, you know, just be aware of that. Also notice here that we don't have any denominators on the first two terms, but really we do, because you could put in a 1 factorial, but 1 factorial is 1. And something I need to do after we're done with this problem is we're going to write a formula for a series at some point. And when I do that, I'm going to put a 0 factorial there, which seems weird, but I'm going to point out again that 0 factorial is 1 by definition. Okay, so we could really put factorials there, but we don't bother right now because the value is 1. So we don't need to write it. Okay, so this is P3. Okay, again, all we need to calculate though are certain values here. This is a number, this is a number, this is a number, and this is a number. Okay, so we need to calculate those derivatives. We need to compute some derivatives. All right, and I do this in a table, so it just helps keep things organized. Newton Alta will not show you a table like this, but this is how a lot of people do it. So I make a table, I put n on my table, and then you just number 0, 1, 2, gets a little bit further, 3, right? 0, 1, 2, 3. Why 3? Because we're doing P3, okay? So that's why we're stopping right here. N equals 3, so stop here. Okay? Now, we need f of a, f prime of a, f double prime of a, f triple prime of a. So we need derivatives here. So we're going to calculate these derivatives. So we write like f in parentheses. So in parentheses like that is understood to mean the nth derivative. And this is going to be the nth derivative evaluated at x, which means we're not plugging a number in yet. It's just x. Okay? And then the third column is going to be the fn, and that's where we're going to evaluate it at a in general. But what is RA? For this problem, a is pi, so we're going to put in a pi, because that's what a is. Okay? Now the other thing you need to do to get started is to know what to put in this first box here. And so what you put right here is the 0th derivative of the function. The 0th derivative of the function is just the function. So you put in sine 2x, okay? And that's just, you just put in your f of x. That's where the function goes. Okay? And then what you're going to do is now we're going to fill out the rest of this table by taking derivatives here. Okay? So in this column, you are taking derivatives. And in this column, what you're going to do is you're going to plug in x equals a, which is pi. All right, so let's do this. So we have sine 2x, and we need to be taking derivatives. So the derivative of sine 2x is cosine 2x, but then the chain rule makes me multiply by 2. So I'll put it there. And then I need another derivative. So the derivative of cosine 2x is going to be negative sine x, negative sine 2x, and then times a 2 again. So overall, negative 4 sine 2x. One more derivative. The derivative of sine 2x is going to be cosine 2x times 2 again. So we're going to have negative 8 cosine 2x. So those are my derivatives. Then what we're going to do is we're going to be plugging in the x equals a, which is pi. So we're going to plug in x equals pi here to all of these. So the first one's going to be sine 2 pi. What's sine 2 pi? Well, 2 pi is where 0 is. So sine of 0 is 0. Then we're going to need 2 cosine 2 pi. Cosine 2 pi is 1, and then we're multiplying by 2, so you get 2. Then you have negative 4 sine 2 pi. Sine 2 pi is 0 again, so this is another 0. And then we get negative 8 cosine 2 pi. Cosine 2 pi is 1 again, so this is just negative 8. All right? Now, this is everything we need to write down the P3. But I just want to be really clear about this. In terms of the formula here, those highlighted things, the f of a, the f prime of a, f double prime a, f triple prime a, those are what we just calculated, okay? So this right here, this is the f of pi, okay? And then this right here, this is the f prime of pi, which we need. This right here, this is the f double prime of pi. And then this right here, this is the f triple prime of pi. And so these 4 numbers that we calculated here are the same as the 4 highlighted things up there in P3. So let's do this then. So what we've got is this. So P3 I wrote out in general, but for us at pi, it's f of pi plus f prime of pi, parentheses x minus pi, right? Pi is like all the a's are pi, plus f double prime of pi over 2 factorial x minus pi squared, and then f triple prime of pi over 3 factorial x minus pi cubed. So let's fill in everything, right? Like these are the numbers that we just calculated, but well, let's write them out. So what do we get? So what we get here is this. We have P3 of x is f of pi. What's f of pi? From our table, it is 0 plus f prime of pi. What's that from my table? Right? We're looking here. So it's 2. 2 x minus pi plus f double prime, so that's here, that's a 0 over 2 x minus pi squared plus f triple prime of pi, that's right here, negative 8. So we have negative 8 over 3 factorial. You have to calculate that at some point. 3 factorial is 1 times 2 times 3, so it's 6. And then x minus pi to the 3. That's P3. all you would do is you would just write it, maybe a little bit nicer, and all that's going to be left are a couple of terms. Some of them are 0, right? But this one's not 0. This one's not 0. The other two are 0. So what you get is 2x minus pi minus, it looks like 8 over 6 is 4/3, x minus pi to the 3. And this is your P3. So that was what we were trying to calculate. Now, what is supposed to be true about it? This is supposed to be the best third degree approximation of, what was the function? Sine 2x. The best third degree approximation of sine 2x for x values near, what was it? At pi, right? Near x equals pi. That's what it's supposed to be. Let's see if it is. Let's see if it is. So let's go try to graph this. So how do I do this? I press this, I do this. Okay. So let's make this a little bit smaller, and then let's make this a little bit bigger. All right, so let's try to get this plotted. So get rid of that. Let's change this. So the function we're approximating now is sine 2x. Neat. All right, and the point we're doing this at is pi, I believe. Pi, where's that? Oh, over there. All right, so there's pi 0. So this is where we're centered at. And then what we want to try to do is plot this P3. So what's P3? I'll even call it P3. P3. All right, here it is. P3, what is it? So it's supposed to be 2 parentheses x minus pi. Now notice that it's already following the curve, right? The reason it's already following the curve is because if you only do that, that's actually the linear approximation. But we did a third degree approximation. So the third degree, let's add the third degree term, minus 4/3 parentheses x minus pi, x minus pi, close 3. Look at that. So do you see how that actually does a really good job of following the curve now, right? That's better than P1. I'll even draw P1 back in. So we didn't try to calculate P1, but you just kind of get it on accident. So like P1 was just 2x minus pi. I didn't have the x. 2x minus pi. Close. All right. So like think about it. Look at those 3 graphs, right? So the red graph is the original function. The black graph is the linear approximation, and it is close, right? Like if you're close by to pi in a section here, the black curve follows the red curve pretty well. But the black curve moves away eventually, right? Moves away from the red curve. The blue curve, on the other hand, follows the red curve further. And that's because it's the third degree approximation. If we did a higher degree approximation, it'll follow it even more. In fact, we didn't calculate a 5th degree, but we could. If we did, it would start out the same. So it would be 2 parentheses x minus pi minus 4 over 3. That's not 4 over 3. 4 over 3 parentheses x minus pi close parentheses cubed. Right, so I have a third degree polynomial. If you add the next one, I'll have to think about it. So what was happening to those derivatives? Oh, I can see them right here. Where are the derivatives? So we went from a 2 to a -8. So the next one's probably going to be a +32. Oops. I'm just trying to guess the formula here. You would not have to do this. Over 5 factorial, which is 120. 120. And then x minus pi. Didn't get the pi. Come on. X minus pi to the 5. All right. So what are we doing here? I just want to change the color. Let's go green. So do you see that? So look over here. So the green curve is actually P5, which is not what we were supposed to be calculating, but we did. But notice that the black curve is the worst. That's P1 at following the red curve. The blue curve is better. The blue curve follows the red curve up to about here. But then the green curve, P5, that one actually follows the red curve up to about here. Well, that's better, right? So notice that the higher degree the polynomial is, the better job it does of following the red curve. The red curve is the original. The others are all approximations. Okay, so maybe let's take this graph and put it in our picture here. How would I do that? Export image. Hey, that looks good. Download. Okay, so let's do a couple things here. Number one, wait for this to load. Okay. Sorry, it's going to take a second here. Come on. Okay, good. Now, close this. Open Notability. Taylor Maclaurin Polynomials. Okay. So let's get our graph in here. All right, here it is. So let's make this a little bit bigger. Okay, so there's a good function. I need to put a box around it because it drives me crazy when it looks like this. Okay. Whoa. Yeah, good enough. No, that's not good enough. I lied. Oh man. Quit. Okay. Oh man. Okay. There we go. So sorry about that. So the idea here was that the red curve, that was sine 2x. And then the black curve was actually y equals P1. And then the blue curve, which we calculated, was y equals P3. I'll say of x. And then the green curve, which we did not ever calculate by hand, was P5. And what you're supposed to notice about this is that the higher degree the polynomial, the better job it does of following y equals sine 2x, right? Higher degree Taylor polynomials follow the y equals sine 2x curve further. All right. And so that's what they do. So higher degree, better approximation of the original function. Okay. Now, before we do anything else, I'll just mention, like, why would we even care about these? So one reason to care about them is because it really is necessary for computers to be able to evaluate strange functions. Okay, there are many reasons to use Taylor polynomials. One is for computers, or to allow computers to evaluate functions. So maybe you haven't never thought about it, but think about it. Like if you want to calculate something like this, we're not going to actually do this example, but like imagine trying to calculate this. Imagine trying to compute like a function, like any kind of function. So like let's say like the natural log of the sine of 1. Like, how are you even going to calculate that on a computer, right? The computer only has basic operations that it knows how to do, right? It's only going to know how to add, subtract, multiply, and divide. These are instructions that are like implemented in hardware, okay? So you're trying to compute that, but a computer can only do a few operations, but what's it called? A processor, CPU, I'll say CPU, but a CPU can only do, let's say, addition, subtraction, multiplication, and division. Right? So if that's all you can do are those basic operations, you can still use a Taylor polynomial to do it, because a Taylor polynomial is a polynomial, right? Think about how to compute this. Subtraction, multiplication, subtraction, multiplication, subtraction. X minus pi to the third is just x minus pi, x minus pi, x minus pi. More multiplication. Okay, so you can't compute a complicated function because your computer does not know how to do a logarithm, but your computer can evaluate a Taylor polynomial. So if you can get a Taylor polynomial close to the value that you need, then you can do it this way. So a computer can only do addition, subtraction, multiplication, division, but that's all you need. All you need to compute an estimate of, I'm going to say the same one, pretend we're doing ln sine 1, using a Taylor polynomial. So that's one reason why you might want Taylor polynomial, to make a computer do the calculations for you. Now, in real life, computers may or may not use a Taylor polynomial. They might have better ways. If they do, or if they have another method, the way they do it is they are going to know what is going to be necessary to actually compute this number to whatever precision they need. So like if they need 16 digits of accuracy, then they're going to know exactly they're going to be able to tell whether or not they have 16 digits of accuracy, and they can just keep doing calculations until they achieve that level of accuracy and then stop. Okay. But yeah, you actually need these things in order to do computations. The faster computers get, the less, fakery you have to do, but you still have to do some. Okay, so that's one reason you might need to do this. Okay, Taylor polynomial approximation of a function. All right. Now, before we go too much further, let me mention what a Maclaurin polynomial is. So Maclaurin, very complicated formula here. It's going to blow your mind. Maclaurin polynomial. A Maclaurin polynomial is a Taylor polynomial with a equals 0. That's it. Okay, that's all a Maclaurin polynomial is. It's just a equals 0. So if you want to, you can write down a formula for it, like a special formula for it, but you don't need one. You can just use the Taylor series formula. So like, for example, Pn, if a was just 0, it would be f of 0, f prime of 0. And then it should be x minus a, right? If I'm following the formula for the Taylor polynomial, but a is 0, which means you don't actually need that. You just need the x. So just that. And then f double prime of 0 over 2. And again, it should be x minus a to the 2, but a is 0. So it's really just x to the 2. Like that. And we already know the pattern here. I'll do one more in case anybody jumps here for some reason. Right, then third degree, and you keep doing that right up until you get to the nth degree. They're all at 0, like that. All right, so that's a formula you could use. You do not need it. You can just use the normal Taylor polynomial formula. All right, let's do an example, because why not? Compute, what do we want? Let's say fourth degree. I changed my mind. Third degree, no, you know what? Sorry, we're going fourth. I want it to be different than what we did. Fourth degree Maclaurin polynomial, we're doing Maclaurin. Polynomial for what? Could be anything. Let's just say cube root of x, which is x to the 1/3. Okay? So there you go. All right, so what would we do? Well, we're going to do this exactly the way we did the Taylor polynomial. Make sure you know the stuff. So the a, of course, is 0. Now, you only need to know a is 0 if you're going to use the Taylor series formula. If you use the one right here, you don't need to know a because there's no a. So a equals 0. You need the n. N is 4, right? Fourth degree Maclaurin polynomial. You need the function. I don't know why I called it y here. Call it f of x. All right, so that's what you need, right? So how are we going to do this? Well, you make a little table. What are we going to? Fourth degree, so we need n. We have, wait, hold on a second. We can't do this. I have to change the function. We're going to have divide by zeros all over the place. You can't do this. Sorry. What do we want to do? Let's do. What do we want to do? What's a function, guys? I don't know a function. I don't want to do a polynomial. I don't want to do an exponential. We already did a sine. We could do a natural log. No, natural logs suck. All right, exponential it is. Makes me sad. We're going to go e to the 3x. That's what we'll do. All right. Bummer. Couldn't think of a better function. E to the 3x. Let's do that. Okay, so we need a 4th degree polynomial. So we're going to go 0, 1, 2, 3, 4. Right? Because we're doing a 4th degree polynomial. And then we're going to need the nth derivative evaluated at x. And after we do that, we're going to need the nth derivative evaluated where? At 0, because we're a Maclaurin polynomial, right? 0, because Maclaurin. Okay, so let's try to do this. So remember, the way you start out is whatever your function is, that's what goes here. Not the derivative, like the 0th derivative is the original function, right? So you do that, and then we take derivatives. So the derivative of e to the 3x is 3e to the 3x. Another derivative, 9e to the 3x. Another derivative, 27e to the 3x. Another derivative, 81e to the 3x. Okay, and then we're going to plug in 0. So we're going to get e to the 3 times 0. That's e to the 0. E to the 0 is 1. And then 3e to the 0, 3. 9e to the 0, 9. 27e to the 0, 27. 81e to the 0, 81. I just thought of what I should have done. I should have done like e to the negative x or something. But it's too late now. All right, so we have these. Now, remember what we're doing with these. We have that number, that number, that number, that number, that number. Those are going to be part of our formula here. So the formula for the Taylor, or Maclaurin, in this case, polynomial, we're doing P4. So P4 is going to be f of 0, f prime of 0, x, f double prime of 0, 2 factorial, x squared, triple prime of 0, 3 factorial, x cubed, and then finally 4th derivative as 0, 4 factorial, x to the 4th. And those numbers that I highlighted, remember, are here, 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 here. Right? Those are the numbers. So you just fill them in. So we have 1 plus 3x, right? 1, 3. The next one's going to be 9. So plus 9 over 2 factorial, which is 2, x squared, plus triple prime, that's the next number, 27 over 6, x cubed. Last one, 81. 4 factorial, which is 24, x to the 4th, right? So we put in those numbers. Well, that's it. That is that's P4, right? That's P4. Now we can just double check that this looks the way it should look. Let's go check it. Clear these all out. We're not going to plot the whole thing. What was my function? E to the... Where's an E, man? Do you think E is just E? Yeah, it is. All right. E to the x. Was it e to the x? E to the 3x. 3x. All right, there it is. Now this is a Maclaurin series, so we did this at 0. So we're at, I think it's 0, 1 here. There it is. So this is where we are doing our approximation. So let us, let's do this. So what is it? It's down here. So P4 is 1 plus 3x. Notice that it's already following the curve, right? That's actually the first degree Taylor polynomial there. Then we got plus 9 over 2, 9 over 2, 9 over 2 x squared. Again, notice that it got better, right? Every time I add a term, the curve is going to do a better job of following the other curve. Plus 27 over 6 x to the 3. See, look, it just gets better and better, doesn't it? Last term, right? We got one more. Plus 81 over 24 for x to the 4. All right, so there we go. That's P4. And again, oops, not what I was trying to do. If you go further away, right, like over here, the green curve and the red curve are nowhere close. But around 0, let's zoom in here. Around 0, look how close they are, right? You can't even tell the difference. And that is the point. Right, so let's, do we want another picture of this? Let's do a picture. Export image. Sure, why not? Download. Download. Let's put it right here. Okay. All right. So what do we got? We've got the red curve, which is y equals e to the 3x. And we've got a green curve, and the green curve is y equals P4. And of course, what you can see is that in this range, very close together. All right. And that's what we're doing when we're doing these. That is what we are doing when we are doing these Taylor series. We're not doing Taylor series, I lied. We're doing Taylor polynomials. Okay. All right. So that is how you do, that's how you compute Taylor polynomials. Okay. So let me see, what else are we doing here? Almost nothing. But okay. Well, I think what we have left to do here is we need to talk about Taylor and Maclaurin series now. We talked about polynomials, now we need series. All right. So Taylor series. All right. Now the nice thing about a Taylor series is that it's just a polynomial, but instead of stopping at degree n, you just keep going. So like we know the higher the degree, the better Pn is at following the curve for y equals f of x, right? We saw that. Increase the n, you get a better approximation. So the idea with the Taylor series is let's just go forever. So let's do an infinite degree Taylor polynomial. Just keep going and don't stop. That's what a Taylor series is. All right, so yeah, so let me write a definition here. definition. Provided that function f of x has derivatives of all orders at x equals a. Now, why am I saying that? I shouldn't put a period there. We're not done with that sentence. Why am I saying that? Well, think about it. Look at the table that you have to fill out, right? If you're doing a Taylor polynomial, you have to do all these derivatives. Well, you have to take all the derivatives first of all, and after you take all the derivatives, you have to plug in the a. Well, if we're going to do this to infinity, then we're not talking about like 4 derivatives. We're talking about first, second, third, fourth, fifth, keep going, 100th, 500th, 1000th, millionth, billionth. All of those derivatives have to exist, and you have to be able to plug a into them in order to get your infinite degree Taylor polynomial. So you need derivatives of all orders to exist, otherwise you can't even do this. Okay, provided that the function f of x has derivatives of all order at x equals a, then the Taylor series, so series now, for f of x centered at or about x equals a is given by, here we go. All right, so here it is. So f of x equals, and I'll talk about that in a second. So we have f of a, we know the formula, f prime of a, x minus a, f double prime of a, 2 factorial, x minus a squared, f triple prime of a, 3 factorial, x minus a cubed. And instead of stopping at n, you just keep going forever. That's it. Or you can write it in like series notation, and you can say n goes from 0 to infinity. And if you think about like what one of these terms looks like, what they look like is they're all an nth derivative evaluated at a over an n factorial, and then x minus a to the n. All right, that is a Taylor series. Okay, now what about this? Okay, so the property that a Taylor series has is, provided this Taylor series exists, right? Because it might not exist, it has to have derivatives of all order. But provided that the Taylor series exists, it's actually equal to the function. Okay. Yeah. Yep. I need to say something a little bit more about that, but give me a second here, and then I will. What am I doing? Clicky, clicky, clicky. All right. So, so this is what a Taylor series is. You generally are not going to be calculating an entire Taylor series, very often. You don't generally need to know what the formula is or anything like that. Generally, what you're going to be doing is you're going to be calculating Taylor polynomials, and if you're going to be working with Taylor series, then they're generally going to give you the Taylor series that you're working with. Okay. All right. While we're at it, here's another theorem here. I had nothing to add to this definition, by the way. I just looked it up, and theirs is not any different than mine. So what we can say is Maclaurin series. Maclaurin again, very complicated definition. A Taylor series with a equals 0. Okay. Now there is a theorem here. I'm not going to do anything with it. They do not prove it in your book, nothing like that. They just tell you it. But here's a theorem. So this is what we would call a uniqueness theorem. Math is full of uniqueness and existence theorems. So they do what it sounds like. If you need to show that there's only one of something, that's uniqueness. And if you want to show that something exists, that's existence. So this is a uniqueness theorem. So it says if f has a power series that converges to f on some interval, containing a, then that power series is the Taylor series for f at a. So what this is saying is if you ever had a function equal to a power series, then the power series is automatically the Taylor series, even if you didn't use the formula here to calculate it. So like an example of that would be like this. So recall the geometric series, right? Here's a geometric series. It's, what is it? So if you have a plus ar plus ar squared plus ar cubed plus dot, 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 dot. That's a geometric series, and it converges to a over 1 minus r, right? If the absolute value of r is less than 1. So that's a geometric series formula. Well, what if I just put in, I can put in whatever I want for x. So what if I use, what if a equals 1 and r is x? What would that do? I'm just going to rewrite this. So I'm going to rewrite this. If a is 1 and r is x, this is 1 plus ar, which is x, plus ar squared, which is 1x squared, plus ar cubed, which is 1x cubed. So we have this series, right? If I just put in those values for a and for r. Well, what's that going to be equal to? It's going to be equal to a, which is 1, over 1 minus r, which is 1 minus x. And that's going to be true if the absolute value of x is less than 1. So what does that say? The interpretation of this from that theorem is going to be this. From the uniqueness theorem, the Taylor series of f of x equals 1 over 1 minus x. Actually, it's not even the Taylor series, it's the Maclaurin series, because I can see that it's centered at 0. Maclaurin series of f of x equals 1 minus x is 1 plus x squared plus x cubed plus dot, dot, dot. Right? Because I have a series, power series, I should say, power series equal to a function. And the uniqueness theorem says if you ever have a power series that converges to a function, then it is the Taylor series. Power series is the Taylor series. So even though, like, I came up with this, like what we have here, for f of x equals 1 minus x, the polynomial is 1 plus x squared plus x cubed. I didn't come up with that using the formula for a Taylor series. But it must be right because according to the uniqueness theorem, there's only one series that is the Taylor series. So if we found a series, it's the Taylor series. It's the only way, it's the only thing it could be. So that's the uniqueness theorem. So I think we're almost done. We're almost done with this. I just want to mention a couple types of, well, one type of problem that your book makes you do here. And then we'll stop. So we don't actually, like I said, do calculating power series or Taylor series in this section. But you need to recognize if you're looking at a Maclaurin series or a Taylor series. So problem type. Recognizing a Taylor series when you see one. So the idea is this idea. Taylor series have a certain formula. Right? It's this one. Fn a in factorial x minus a to the n. And what you're going to recognize about this is that the a matches the a. Those need to match. And also, there's an n, and an n. Right? So the a matches the a, and the n's all match. And all three n's match in the formula. Okay, so what they're going to do is they're going to give you something and they're going to ask you if it is a Taylor series. And it's particularly important that you understand this because Newton is wrong about this and it drives me crazy, but it is what it is. So here's an example of what I'm talking about here. The series, here's a series, e squared over n, x minus 2 to the n, from 0 to infinity, is an example. Actually, that's not how they word it. They say, for some reason, they say at x equals 2 is an example of a Taylor series. And it's true or false. All right. Now, here's what Newton wants you to do. Okay. What Newton wants. Okay. Compare this and this. Oops, there's an in there. You want to compare those and just notice that they're different. For example, one has in and one has in factorial, and so they are different. So they want you to say false, because they're not, it's not a Taylor series. Okay, that's what they want you to do, just to notice that that's wrong. It doesn't match the formula. Why that? Now, why Newton is wrong? Why Newton is wrong. Anything any part of the derivative, any part of the fn of a might cancel out the n factorial, and you would still have a Taylor series. So really, any power series is a Taylor series. Well, if it converges, is a Taylor series for something, for some function, even if you don't know what it is. Okay, so mostly what they want you to do is recognize where the problem is different than the basic formula for a Taylor series. And if you notice a difference, then you're supposed to say it's not a Taylor series. That's bad, right? Because we know from the uniqueness theorem that any convergent series, if a convergent power series is equal to a function, then it's the Taylor series for that function. Well, every power series that converges is a function. So every power series that converges is a Taylor series. So Newton has the wrong answer on every single one of these problems. So again, what you're supposed to do is just compare what they give you to the basic formula here, and if it is different, you say false. And if it is the same, you say true. Okay. So I think that's it for this section. There's going to be 2 more videos for this, and homework due later on. So good luck with that. See you in the next video.